All right, this is a video that summarizes the hypothesis testing for a single population. So we're going to be looking at the three different ways essentially that this can happen and how do we know which one to choose. So a hypothesis test is a way to draw inferences about populations based on samples that we've taken from those populations. Here are the basic components of a hypothesis test. First, you state your null hypothesis, which is usually just a restatement of that the population mean has not changed. So if it was 80 for the population mean, we would say the mean is still 80 for mu. The alternate hypothesis is going to be based on what we saw in our samples. So we're going to be making either a statement that the population mean might be greater than 80, less than 80, or possibly just different, which could be either direction. And then we'll have a level of significance that is attached to our test, usually 0.01 or 0.05. Then we're going to determine the sampling distribution to use and calculate the appropriate test statistic because our p-value that we're going to need is based on our test statistic. So here are the three categories essentially that we looked at in our classes. So testing about the mean, which is mu, the population mean, when you actually do know your population standard deviation. Testing about the mean mu when we don't know the population standard deviation. So in other words, we would have the sample standard deviation only, not the actual population standard deviation. This one's the more common test. We usually don't have the information about our population, but it is a little bit harder one to read because we have to use a different table. And then the third and final one that had a single population was testing about a proportion P. Remember, a proportion P is not the same thing as a mean. A mean is an average, so you take all your values and divide by how many you have, whereas a proportion is, remember, a binomial experiment where you have a probability of success and failure, where P is the probability of success. So a certain number of successes out of a certain number of trials. And remember, those trials are independent. So if we look at the first case, so if I know that I have my population standard deviation, things that you must know to proceed. We must know that the distribution of our original set of data is normal, or if we have at least a sample size larger than or equal to 30, then we can use the central limit theorem and go ahead and proceed. We use the normal distribution for the test, and our test statistic is a z-score. This is the formula for calculating that z-score, the sample mean minus the population mean all over the standard error, which is the population standard deviation divided by the square root of the sample size. Remember, that was for that X bar sampling distribution. And then if we have, we're also looking at a mean of mu, but we do not have the population standard deviation. So we have the sample standard deviation instead. We still have to know that the original distribution is normal, or we have to have a sample size that is larger than or equal to 30 to use the central limit theorem and proceed. This time, though, we use the student's t-distribution for our test, and our test statistic is a t-score. So notice the formula looks very simple, simple and easy, just pretty much the same as the z-score formula, except we're plugging in sample standard deviation when we do our standard error down here. The big difference is we're reading off a different table, and that table also requires us to know the degrees of freedom, which is the number of items in your sample minus 1. And if you don't see that row of value in your actual student's t-table, remember we round down to the next degree of freedom in the list. And then our final one, like we said, is the binomial experiment ones where we're doing a proportion P. You must show that your sample is large enough to approximate using the normal distribution. So that is that requirement of number of trials times probability of success and number of trials times the probability of failure for the population, because those are P and Q for the population. Those both have to, but N is the sample size. Those have to both be greater than or equal to 5. So if we have that condition, we can proceed. And we'll use a normal distribution for the test, and our test statistic is a z-score. Before you can calculate your z-score, you'll need this p-hat value, which is for your sample. That's the number of successes you saw in your sample out of the number of trials. And then this is the formula for the z-score when you're dealing with proportions. It's the p-hat, which is this value right here, minus the probability of success for the population, and then divided by the square root of the probability of success times the probability of failure for the population divided by the number of trials. Okay, so that's a lot of information. Let's go through some different scenarios and examples after we finish our steps. So yeah, this was just figuring out your sampling distribution. And honestly, once you get this part of hypothesis testing down, the last 3 steps are the same every single time. You look in the appropriate table for your test statistics and you find your p-value, or you estimate the p-value if you're using students t, because it'll be between two values usually. If your p-value is less than or equal to your level of significance alpha, we will reject our null hypothesis. If the p-value is greater than our alpha, we do not reject our null hypothesis. In other words, we say there's really no change from the original previous study. Interpretation of the results includes making a statement about whether the data is significant or not at that level of significance set by the problem. So if we reject the null, our data is significant. If we do not reject the null, our data is not significant. So I have that there. Then we state either that there is or is not enough evidence to believe that the alternative hypothesis is true at our level of significance. So if you reject your null, you are saying there is enough evidence to believe the alternate. If you don't reject your null, you're going to say there is not enough evidence to conclude. So again, I've kind of restated that part right there. All right, so let's look at our first example. It says, suppose we are conducting a hypothesis test to determine if the average time spent by students on homework has increased compared to the historical average of 40 minutes. So by it saying historical, that's previous studies. That means I'm going to go ahead and underline this historical average. That means the previous population mean was reported as 40. So that's notice population mean. Population standard deviation of homework time. So notice population standard deviation is known to be 20. Okay, so they give us that. A sample of 30 students, so we're just taking note of everything we see, was monitored for a month, and their average time spent on homework and the sample mean was reported as 55. So that's the X bar. So that's for that sample. Test at the 5% level of significance. Kind of just taking note of everything that they gave us. So the question is not at the end this time, but it is at the beginning. Suppose we're conducting a hypothesis test to determine if the average time spent by students on homework has increased. Okay, so that's going to help us with our alternate. So our null, which we call, remember, H0, when you're doing a single population test, you just restate the population mean. So we say that the population mean is 40, that no change has occurred from the past. The alternative here is that it looks like they're studying more than the historical data. So we're going to be saying not that it's equal to 55, but we're just trying to say, is the population mean greater than that original 40 that we had historically? Okay. Our alpha is the 0.05. And because we're doing a greater than, and this is a single population, remember that's going to correlate nicely with a single tail to the right. So this is a right-tailed test. Okay. All right, what distribution are we going to be using? Well, the big things to check. Is our sample size large enough, or did they tell us somewhere in the problem that the distribution of time spent on studying for homework is normal or bell-shaped or symmetric? The sample size is 30, so we're good there. So our N is greater than or equal to 30. So that means we can proceed with that part. And population standard deviation is known, which is our sigma. That means we're going to use the normal distribution. So that determines, remember, our test statistic formula. So our test statistic formula is going to be Z equals X bar minus population mean, so sample mean minus population mean, over population standard deviation divided by the square root of the sample size. So let's plug in our values. So that's going to be 55 minus 40 over, the sigma was 20, and then square root of 30. So let's pull up my calculator and let's calculate that value. Now, I don't have a fancy one on my computer, but we can use parentheses appropriately. So 55 minus 40 is all on top. And then we're going to divide that by the parentheses of 20 divided by, and I have to type this in a little funny on the computer calculator. I type in the number and then hit my square root of that. And then I want a parentheses to close out the denominator. So I get that that is a test statistic of, if we round to 2 decimal places, which is what we usually do for Z, we usually go to 3 for a t-table, I get about 4.11. Now, remember what this is referencing. This is the normal bell curve, and we're saying our test statistic, that's this guy, is at 4.11, which is pretty far in that right tail. The p-value is going to be what we get from reading the chart, that probability chart that correlates with a right tail of that value. So I've got my statistics tables pulled up. And let's go down the z's. These are all the negative z's. So look, our z table doesn't even go to 4.11. It stops at 3.49 actually. So it says for z values greater than 3.49, use 1 as the approximate area. Now you have to remember the table always tells you area to the left. So what they're telling you is that this part over here is approximately 1. Okay, because remember, table gives us area to the left. So we get the area of the right by doing 1 minus the area of the left. So this is actually a p-value of 0. The probability would be so small if you wanted to write it to 4 decimal places like they do on, you don't have to, but if you wanted to, you could, or you could just say 0. The p-value is so tiny and so far out there on that right tail that it's pretty much almost an impossible event. Now, how does that relate to our conclusion of this test? Well, if your p-value, which ours was 0, is less than or equal to your alpha, which was at this test, remember, was a 0.05, that is definitely true. 0 is less than 5%, because remember, these are probabilities which relate to percents. We reject the null. Okay, so that is the conclusion. Now, just because it's quicker for me, I'm going to type out what that means in terms of the interpretation. So we're rejecting the null, so we would say the data is significant at the 0.05 level. We have enough evidence to conclude that the null is not true anymore. We're rejecting the null. So we're going to state that as how they reworded their question, which was the average time spent by students on homework has increased to more than the 40 minutes. Okay. All right. So that part is our interpretation statement. All right. So we're going to do 2 more examples because, like I said, I wanted to do kind of one of each. This video may be a little longer than our normal ones. But let's look at example 2. It says, suppose a researcher is investigating the proportion of students who pass a standardized test. The success rate in the past is known to be 0.80. Recently, he sampled, 100 students and determined that only 75 students passed the standardized test. Is there reason to believe that the pass rate is now lower than what the historical data was? Test at the 5% level of significance. Now, this is not a mean. Nowhere did he say that the students scored a specific grade on the test as the average grade. This is a proportion of students who pass the exam. So it's either a pass or a fail. That means we're dealing with a proportion. So we have a P of historical proportion, that's our population, in the past about 80% success. So that means our Q in the past has been, for the population, 20%. Because remember, this has to add to 1. He has this sample of 100 students, and the number of successes in that specific sample was 75, which means my P hat, which is our point estimator for that sample, is going to be 75 divided by 100, or 0.75. So notice less than the historical previous success rate, but is it significant enough? So we're going to be testing this at the 5% level, and we're looking for, is it now lower? So that's going to help us with our null and our alternate. So H sub 0, which is the null, is that the proportion hasn't changed. So it's still 80% pass rate overall. Whereas the alternate is, we're seeing now that less students in this sample actually passed. So he said, is it now lower? So we're saying, is the P lower than that historical data? The alpha is the 0.05 again. And we're going to talk about what distribution to use. Well, because this is a binomial experiment with a proportion, we have to show that n times the p is greater than or equal to 5, and n times the q is greater than or equal to 5. If we can show that, then we can use the normal distribution as the approximate for the binomial. So we have 100 times the 0.8. That's definitely going to be greater than or equal to 5. And then we have 100 times the 0.2, which would be 20, which is also greater than or equal to 5. So we're good. So we can use the normal distribution. So remember, proportions use the normal distribution, but you have to show that you have the large enough sample size related to those probabilities of success and failure. All right, so we're going to find our sample test statistics. So I've already got everything I needed written off to the side. So I've got Z is going to be P hat minus the P all over the square root of the P times Q divided by the N. So P hat was 0.75 minus the 0.80. Sometimes I like to write them in the same number of decimal places. The bottom is the 0.8 times the 0.2, which is still the 0.80 and the 0.20. And then we had a sample size of 100. Okay, so we're going to get a Z-score for this. So let's work it out. So parentheses for my top, 0.75 minus 0.8. Close my parentheses, divided by, open a parentheses. And then this is where things get a little crazy for me. I'm going to open a second set of parentheses for the everything I'm going to type in that I want to be in that square root. So 0.8 times 0.2 divided by 100. Close that set. That's inside parentheses in my denominator. So I'm going to be taking the square root of that part. So notice if you see my calculator here, hopefully you can see it. That square root symbol is just on that parentheses part, and then I close my parentheses for my denominator. So if you have your calculator and it does this a lot easier than mine, that's wonderful. But I get a Z-score of negative 1.25. Okay, so we're going to go to our Z table. This is the positive Z, so we need to go back up to the negative, and we're going to find negative 1.25. So here's the 0.05 category, and then I need to go down until I'm at negative 1.2, and I get this 10.56 right there, or sorry, 0.1056. So my p-value, and we're doing a left tail because we're doing lower than at negative 1.25 is 0.1056. Okay, so there's my p-value. You can write that there if you want to write it out to the side and circle it. So our conclusion, well, if our p-value is less than alpha, we can reject the null, but our p-value of 0.1056, our alpha is 0.05, that is not less than, it's greater than. So we cannot reject the null. So that means if we do our interpretation, so let's type this up, the data is not significant at the 5%, or you can put 0.05 level. This means we do not have enough evidence to conclude that, and then this is where you go back to your problem, the pass rate is now lower than the 0.8 for the population. Okay, so there is our statement for that. And then the final one for this first video over hypothesis testing is going to, of course, probably be the T, because we haven't done that yet. So it says, suppose a company manufactures light bulbs and they want to ensure that the average lifespan of their light bulbs is consistent with industry standards. The industry standard is that the average lifespan is 1,000 hours. So that's going to be the industry. That's going to be previous data. So that's our population mean. The company takes a sample of 30 light bulbs, and the mean for that sample is 985 hours of working lifespan. And then the standard deviation, though, is pretty large. It's 350 hours. Does this indicate that the average lifespan of their light bulbs is different either way from the industry standard? And then we're going to use a 0.01 level of significance. So our null is that everything's the same as the population mean. Our alternate, though, is that it's different either way. So that means we just do a not equal to, and that number is a two-tailed test. Okay, and our alpha is 0.01. Okay, what distribution will we be using, and explain why? Well, we know that our sample is greater than or equal to 30, so it doesn't matter if they tell us if it is originally a lifespan is, bell-shaped and symmetric, because we have a large enough sample size, and standard deviation, sample standard deviation is known, but population standard deviation is not. That's the key. Population standard deviation is not known, so that's when we say we need to use the student's T distribution. Okay, so finding that test statistic, the formula doesn't change really much, except just, what values we're plugging in are called different things. So we have our sample mean minus our population mean, and then on the bottom, it is the standard deviation of the sample divided by the square root of n. So that's going to be 985 minus 1,000 over, and then our S is 350 divided by the square root of 30. Okay, so let's see what we get here. So 985 minus 1,000. I should have put that in parentheses, but that's okay. Divided by parentheses, we have 350, and then it's divided by the square root of that 30. So 30 square root, close the parentheses, and we get that is negative 0.235. I usually go to 3 decimal places when I'm dealing with the student's T. Okay, so this looks like I'm not probably going to reject my null, but let's go ahead and go back to our T table and show our p-value. So we got to go down to students T. Now remember, the students T distribution gives everything in positives, but we are doing a two-tailed test, or even if you're doing the one-tailed test, you can mirror the right tail and left tail have similar values. They just have a negative versus a positive on the score. So when we go to, let's go back to our notes. Let's draw a picture. We're talking about from negative 0.235, and we've got positive 0.235. And our p-value area is going to be everything to the left and right of that part, because those are our two tails for our sample. Now, obviously, I don't think that's going to pass our level of significance that we had, but we need to show that. So when you go to look this up in the table, we need our degrees of freedom. That's the part we didn't write down. So our degrees of freedom was 30 sample minus 1, which is 29. So we need to go to that row in our table, which I'm going to just highlight here. That's this whole row. 29 is right here. And we have, remember, to figure out that we're doing a two-tailed test. So this is going to be the column up here that we'll look at in just a second. Okay, two-tailed area. And then we locate down here where our test statistic is. Now, remember, these are getting bigger as we go from left to right, whereas the percentages are getting smaller from left to right. So when we look at this, this is 0.23 or 0.24 if you want to, round it, but it's 0.23. That is not even on the table. So 0.235, because remember the positive and negative, they're going to be equally spaced on each side. So when we go up here to interpret that, notice that for our two-tailed test, what that means is our area is going to be actually greater than or equal to that 0.5, 50%. So our p-value is greater than or equal to 0.50, okay? And that's according to that estimation that we're using. So more than 50% of the table would be shaded in. And we don't know if it's, 60, 70, 80, it's just more because we don't have any other scale on the other side of that number to get like a cap for the top part since it was completely before any of the values. So what we get from this is that since our p-value, which is 0.50 greater than, that's the smallest it can get, or bigger, is greater than our alpha, which in this problem was 0.01, so way bigger than that, we cannot reject the null. Okay, so we're going to write our conclusion statement. The data is not significant, or hang on. Yeah, I want to say it like that. At the 1% level, this means there is not enough evidence to conclude that, and then we go back to our statement, which was they were testing that the company's light bulbs are different either way from the industry standard average of 1,000 hour lifespan. Okay. So we have shown 3 different versions of hypothesis testing with a single population in this video. I hope that helps.